And Angela Boltasseva, she is the distinguished professor of Purdue, at Purdue University, United States. She is the fellow of NAI, MIS-IEEE, Optica and SPIE. Today, she will talk about material-driven photonics toward tunable and extreme light control. Let's warmly welcome.
Thank you very much. Thank you, and I would like to start by thanking, of course, the organizers of the conference and Ortwin and Said for making this spectacular event. As I mentioned yesterday, Meta has a special place in my heart. It's always nice to meet friends and colleagues and to connect in beautiful places around the world. So today I would like to talk about two layers or two knobs that we can tune when we are looking into enhancing light-matter interactions, and namely design and materials. And I'm going to present work which is based largely on the research that is done at Purdue University, largely in collaboration with my dear colleague and husband Vlad Shalev, but also with Alex Kildyshev at Purdue, and some external wonderful collaborators that are listed here, Igor Bondarev, and I strongly suggest you to visit talks that are presented at this conference, Jacob Kurgin, Ariga Calzolari, Bivar Saha, Doug Nettleson, Yuri Gagotsi, and Federica Capassa as well. And Marcella, I'm sorry that I'm not mentioning it on a slide because I'm not going to talk about this work, but Marcella Ferreira is also presenting a lot of work which is related to exciting photonic materials. So what I will start with is, again, just a few words of kind of our overall motivation. What is it we are looking into when we want to do something fun, both fundamentally but also on the device level? How do we enhance light-matter interactions? And I'll just give you some examples or some highlights, some avenues of excitement that we are sharing at Purdue, looking at both material component and the design as well. So example of materials that we are looking into would be transition metal nitrides, and these would be materials that are known to many in this community because they are behaving as noble metals in application in plasmonics and nanophotonics. And specifically, I will talk about a very interesting regime of operation of these materials when we actually thin them down so that they reside somewhere in between conventional thin films and true two-dimensional materials. We call them transdimensional regime as well. And what I would like to show here is that the second we switch to a new material platform, many wonderful things can pop up. And I can tell you that we started with tunable and tailorable plasmonics, and then we ended up exploring the regimes of strongly correlated electron interactions. So every time you choose a new material platform, new physics might open up. I will talk a little bit, just a tiny bit, about the design and how we combine advanced design of the cavities with two-dimensional materials, the mainstream 2D materials, and I would rather refer you to my other talk today to hear about this work. Briefly mention our work on transparent conducting oxides, which is actually emerging as one of the most interesting materials for switchable, tunable, and space-time photonics that my colleague Vlad Shalev will actually be covering in his keynote. And very briefly introduce a new class of materials that I think hold a lot of promise in the area of photonics. Okay, so we start with our holistic approach to enhancing light-matter interactions. And usually in this community, what we've done, we kind of started with well-established material platforms, and then we looked into different ways of introducing, resonators and cavities and, concepts of a matter surface, and maybe looking into some interesting regimes that we can achieve by this smart design. For example, interference effects based on like phonoresonances or bound state in a continuum or a strongly coupled regime. So this is all blooming, but another layer that we should not forget about and rather utilize more actively is actually the foundational layer. Well, here it says a second layer of materials, but I would rather say the foundational layer is which materials we're actually choosing to implement all those concepts and all those devices. And here there is no really shortage of ideas and there is no shortage of materials, right? Because we have so many wonderful candidates to look into different optical properties, different manifestations, different tunability in two-dimensional materials, in metals and dielectrics. We can look at materials that support nonlinear response and also exotic epsilon E0 behavior and much more. And this all of it together, this first and second layer materials and the design of the structures together are driving the development a lot of systems or on application level. We already heard wonderful talks on metasurfaces design and metasurface applications for sustainable energy conversion, for imaging, sensing, and for emerging areas of quantum. We started actually this conference with applications of metamaterials for quantum technologies. And what I want to argue is that we should not forget that, again, switching to a new material system always brings new physics and new phenomena. Okay, so again, as a community, we are blessed with having access to a lot of material platforms that we can play around with in nanophotonics. Whether you want to investigate in all low loss and high index dielectrics for metasurfaces like titanium dioxide we all know about, or you start with noble metals that we've been exploring in the area of plasmonic for decades, or you want to explore this very interesting region of epsilon E0 that a lot of talks by Marcel and Vlad and others and Bob Boyd and others covering during this conference. So let's start at this corner and look really what we can do here in terms of interesting materials. And an interesting material that we've been working with for a very long time at Purdue is actually a class of transitional metal nitrides, or specifically titanium nitride. So this material usually behaves as a metal. It resembles actually gold very much. So its optical properties reminds us of properties of gold. So you can use it for all applications of plasmonics. But this material is tailorable so that you can make it compared to gold. This is a real part of dielectric permittivity for gold. You can make it more or less metallic, just depending on different parameters. You can play around with stoichiometry, you can play around with deposition conditions and other things, while the material loss remains basically the same. Most important thing here is that with the new materials that we introduce in the area of nanoplasmonics, we open up new regimes of both fabrication and also material synthesis. And for titanium nitride specifically, you can actually grow it epitaxially on a range of substrates. So growing really, really thin, really, really smooth metallic films is difficult. Here it actually happens just because you have a lattice match. And it makes it possible to actually go down to thicknesses that are very, very small. And it's been shown, it's actually predicted by many theoretical works and then later shown experimentally, for example, by Javier Garcia-Abajo, that if you go to extremely thin films, wonderful, wonderful effects would happen, simply because the metallicity of your materials will change, and then you can have this tailorable or tunable plasmonic response. So let's look what happens if you go to ultra-thin titanium nitride films. So we were able to go down to 1-2 nanometers. Again, this is only possible simply because you have this high degree of epitaxiality. You don't have any islands, you just grow something on a lattice match substrate. And going down to 1 nanometer means that you are actually left with about 5 atomic layers. So it's really transitional regime between conventional thin films and true two-dimensional films. What we found out that actually this is a totally different regime of operation. As I said, it resides somewhere in between, but it opens up a lot of opportunities, both for new optics and, as I show later, for exploration of new physical effects as well. Well, first of all, as was predicted and shown by Javier and others in the field as well, you get access us to extreme sensitivity and tunability of this material. So basically, when you're going to such extremely thin layers of metallic materials, you become sensitive to all the external stimuli. Electrical or optical, you get enhanced nonlinearity, you get quantum effects. Tunability and switching is what we're after, right? We all want to operate around the point where you can switch between different operational regime and achieve some interesting functionality, which can be either electrically or optically tuned. So we call this transdimensional materials, or transdimensional photonics, and got very excited about that. So the first demonstrations that we did is obviously just to see how the optical properties are changing. What we showed that indeed in the ultra-thin titanium nitride films, you have a lowering metallicity with a reduced thickness. But in this specific case, films do remain metallic until they're very thin. We worked with theory people, and this is a group of Arriga Calzolari who actually ran DFT calculations, showing the same trend as we saw in experiments, that our plasma frequency is changing with frequency, so that again your materials become less metallic when you go to a thinner film, and that is actually can be well understood in the simple terms, because when you have, your bulk material with, let's say, high carrier concentration, if you thin it down, then, when you're calculating the carrier density, then it would be inversely proportional to the thickness. So you actually acquire this dependence on the thickness that you don't have in conventional thin films. And we also showed that in thin films, what happens is that you actually have a band structure change, and that also drives the change in the optical response. Igor Bondarev here is what they developed the quasi-classical theory to describe the properties of titanium nitride film in this ultra-thin regime, and show that indeed the plasma frequency actually acquires a special dispersion, which is typical for 2D material. So it's a very interesting effect and very nice description, because you really show the transition from bulk on conventional thin films all the way to truly two-dimensional material. Okay, so what does it bring us? Well, it actually opens up a new realm for exploration, which goes far beyond photonics. And let me actually switch to another material which belongs to the same family. It's hafnium nitride. So this experiment was done by our collaborator in India, Beaver Saha. So hafnium nitride usually is a conventional metal. It's a little less metallic to start with than gold. But it has the same properties in terms of ultra-thin or transdimensional regime. When you thin it down, it becomes less metallic. And let us dig a little bit into what's really going on into these ultra-thin films. So what really happens here is that when the film thickness is decreasing, the electrons start to interact really strongly. So you really have decreased screening. So you start to feel each other through the substrate and superstrate. This increased interaction between charges can actually lead to very interesting things. Well, you have strongly increased electron confinement. The potential would acquire almost in-plane character. But when those experiments were ran on hafnium nitride in the ultra-thin regime, that Igor Bondarev actually came up with the idea to actually explore a very interesting regime of strongly correlated systems that we might actually be seeing in those films. And let me remind you that strongly correlated systems have attracted a lot of attention over many, many years in many communities across physics, because again, these are all the superconductors, these are quantum Hall systems, and very interesting effects connected to metal to insulated transition. This is exactly what people in both semiconductors and now in photonics are seeing, right? So for example, Condon effect and Wigner crystallization. So in very simple terms, what is it we are talking about? So very simplistic quantum mechanical picture here would be that, well, for metallic material or semiconducting materials, for interacting electrons, you have a potential and kinetic energy. So usually for metals, again, we forget kind of about the potential energy because we say that this is almost free electron gas. So electrons are free to move, but not in the case of this transdimensional film. When we try to thin it down, they actually start to reduce the kinetic energy and dramatically increase potential energy of interactions in this ultra-thin film. So if we look really at the dependence of potential energy on the electron-electron spacing, it goes as 1 over r, so it's just, Coulomb interaction, and the kinetic energy is connected to your Fermi velocity, and it actually goes like 1 over r squared. So if you are changing the inter-electron spacing, or if you are changing the density, it means that you are changing and playing around with the ratio of potential to kinetic energy. And playing around with this ratio means that you can enter the regime where your potential energy outweighs kinetic energy, even though you have electrons that are kind of free to move to start with. They actually freeze into the lattice, which would correspond to one of the ground states of the system that's called a Wigner crystal. So it is a very interesting and peculiar regime of operation. You can observe it, or people predicted that it can be observed in 1, 2, and 3D. It is not easy to observe, so you have to satisfy certain requirements for observing Wigner crystals. So the first one is obviously then potential energy have to outweigh the kinetic energy. For that, you have to better switch to 2D systems because this way kinetic energy goes down, right? But you also have to do some tricks and make sure that materials are right? You need high quality materials because you don't want any effects connected to disorder. You want large effective mass, low end, and it's hard. It's hard to find materials, that can do that. So people have succeeded in observing Wigner crystallization in many systems before. But you always have to use some tricks, and some tricks would be, for example, low temperature, really low temperature liquid helium, or two-dimensional electron gas in semiconductors, using magnetic field to actually help you to boost the potential energy. Or you can combine, low temperature with no magnetic field, but use, more structure. Then we are entering a so-called generalized Wigner crystal, where you create the potential to help you to trap electrons. But the main idea, again, that you want to achieve the regime where potential energy it becomes so strong that it actually kind of freezes electrons into the new lattice, and the lattice period of this Wigner crystal would be obviously different than new lattice constant, but that's what actually where electrons are held in place. So very intriguing area, and just flashing what was done in this area before by other teams that I mentioned for other material systems. What was observed in hafnium nitride? So in hafnium nitride, when we go from thin films that are kind of show conventional metallic behavior to something which is below 4 nanometers, you see that the material goes through this metal to insulated transition. It becomes totally transparent. So this is an optical features. But the most important and interesting features are observed in resistivity and what you see in the resistivity and the carrier concentration. The carrier concentration goes abruptly down for thicknesses below 4 nanometers. Resistivity rises. And the intriguing point that really it can serve as an indication of the Wigner crystallization is that when you lower the temperature, usually when you lower the temperature, you would expect the resistivity goes down. Now for these materials, when you go very, very thin, and you lower the temperature, you see the onset of resistivity rise at low temperature. So the low temperature here again is just helping you to localize and freeze those electrons. So this is a very powerful signature of an interesting effect here. So, and this is my last slide here on this topic, just summarizing that when we started to work with these transdimensional materials, and by the way, I don't have time to cover all the interesting effects that transdimensional regime and materials can offer, and I refer to talks of our collaborators and Igor Bondar specifically. But when we started started to work with them as tailorable materials, a lot of other things opened up. And now we believe that this is a very interesting platform for actually exploring this strongly correlated electronic system, because in these materials, and let me call them intermediate carrier density materials, you really reside between semiconductors, 2D films, and metals, because you have access to this great tunability and tailorability of your carrier concentration, which simply can be changed by choosing the right semi-metal and changing the thickness. And then you can control the quality of material, substrate, superstrate, and you will actually find yourself covering pretty much the unexplored areas of this phase diagram that indicates where Wigner crystallization can be observed. So an interesting platform for exploration. Okay, very, very quickly, and I will talk about conventional materials. I talked about materials that bring some interesting effects. Now, you take materials that are already well known, like Van der Waals 2D materials, as there is a lot of body of work on these materials happening right now. But then you combine it with something let's say, less conventional. So what we can do in this realm, if you want to really explore some interesting regime of light-matter interactions, and here what we've done, and I will be talking about it in my other talks today later, is to combine it with a very interesting and intriguing new concept that was actually suggested quite recently by researchers at Technical University of Denmark, where they used dielectric cavities, or dielectric structures that actually simultaneously can provide high quality factor, which is usually what we expect to see in dielectric cavities, and extremely small mode volume, which is usually kind of reserved for plasmonics. So this is a very interesting concept. Again, I don't have time to go into details, but to harness the power of topology optimization, which is also pioneered by Eli Jablonovich largely, and others in the field, we actually can design dielectric structures that would support extremely tightly confined sub-wavelength mode volumes. And this is one of the interesting avenues for designing cavities that you can basically combine with anything. And again, in our work, what we did, we combined it with two-dimensional materials. So this is a collaboration with Harvard team, with Federico, where we designed such a cavity, and this cavity can be combined with basically any two-dimensional materials depending on what is your excitation wavelengths that you're targeting. I'm just flashing this very nice imaging right here to show you the power of topologically optimized structures that you can fabricate in silicon and then put a layer of 2D material on top. Not very pretty, but nonetheless, we did succeed in actually running those experiments, both in terms of very challenging fabrication of these topology optimized cavities and transferring the 2D materials and realizing the photoluminescence measurement and showing the great enhancement of that is actually induced by coupling to this deeply subwavelength dielectric cavities. Again, I won't be talking much about this enhancement here, but rather want to stress again that by combining 2D material with topologically optimized cavities, we again open up new regimes of enhancing light-matter interactions. Going back to this material chart for nanophotonics, I also wanted to very briefly to touch upon conducting oxides that Vlad will be talking about in his talk. We already covered a lot of aspects of transparent conducting oxides and interesting effects on talking about epsilon E0, right? Epsilon E0 effects, largely pioneered by Nader and Gede, Andrea Liu, and others, brings a lot of excitement into this field right now. And the most interesting thing is that we believe that these materials can open up a possibility, an avenue for realizing photonic time crystals. Why do we believe that? We believe that this is the only material platform so far that can support support both ultra-fast and deep modulation of the optical response. Now the question is, how to enhance the response to the very extreme? So what if I really want to drive it to the limit? So driving the response of like oxide to the limits means that I want to achieve really high absorption of light. I want to concentrate my light in the thin layer of oxide and see what's going on. And this is not trivial because transparent conducting oxides are transparent. So it's very difficult to localize light in extremely thin layer. But you really want to do that because achieving perfect absorption in ultra-thin TCO layer would mean that you would drive very high electron temperature. Driving electron temperature very high compared to conventional schemes means that instead of conventional behavior in the change of the refractive index over time, you actually can get access to extremely fast oscillation in the optical response. And you want to achieve those oscillations on a time scale which is comparable to a single cycle. And that's when you can drive the development of interesting concepts such as photonic time crystals. So in order to do this and achieve this high electron temperature, again, you have to confine light in the transparent layer, which is very, very thin. So for that, you can use different concepts. Again, I'm combining material and the design here together. And this concept is a concept of TAM plasmon polaritons that, so we actually got an idea from the work by Timofeyev, where you have basically a Bragg grating and an extremely thin layer of TCO on top. Just to sum up this part, so we designed a structure using based on prior works in this area, but in different configuration. We designed a structure using inverse design. Again, that's the power of combining interesting materials and inverse design, so that you have unconventional distribution of Bragg reflectors that allows you to concentrate actually a lot of light into just 20 nanometers of transparent material. And what you can achieve here, again, you can really maximize the absorbed energy in the azial layer, in extremely thin layer, and then also drive this, by driving this cavity-enhanced absorption, you achieve very high electron temperatures, and that would be the key to achieving ultra-fast response in the time domain. Okay, finishing off, I would like to introduce and mention very briefly, there is another material platform to play around with in photonics that's called MXenes. And MXenes are similar to transition metal nitride that I started with, but it can be a combination of transition metal with nitride, with nitrogen, or carbon. So these materials have been discovered in Drexel University, and they have a very interesting combination. They are quasi two-dimensional. There are many species of them because their properties really depend not only on the composition of material, but also on the surface termination and many other things. So MXenes have emerged as a very interesting hybrid materials for applications in sensing, electromagnetic shielding, and now in photonics, because what they actually have and offer, in addition to their interesting properties that are actually similar to multi-layer graphene, and at the same time similar to transparent conducting oxides that I showed you right now. They offer a lot of tunability and tailorability. So this is just, again, one example of MXene optical response, and I just show it here because it provides us with an opportunity to tune, for example, the zero crossing, the famous epsilon near zero, in extremely wide range for applications in all optical switching or other effects. For those interested in MXenes, since I don't have time to talk about this, I refer to recent Optics and Photonics newspaper. Okay, so, and finishing off, again, since we do have access to so many materials, I wanted to stress that the holistic approach for us, I think that we could find a lot of excitement in, is to not only to think about the design layer, you know, different structures and cavities or metasurfaces, but also try to think about optimizing or designing materials and structures together for looking into new effects, so that we can simultaneously tailor the design and tailor the underlying material platform. And for that, well, obviously, we would need very smart algorithms helping us, and this is outlining the vision for the field where we really would combine our understanding of how we design metastructures with the design of tailorable materials. With that, I would like to thank the entire Purdue team and all of you for your attention. Thank you.
Thank you very much. Yeah. Very fantastic talk. Now open the question.
Alexandra, this is absolutely fantastic talk, and such a visionary talk, and it's really very powerful. I have just one terminological question, or rather comment. You were talking very convincingly about time variable crystals. To be fair to the history of science, they cannot be called time crystals, because time crystals are systems which are analog to conventional space crystals through the time-space duality. And they have been introduced by Frank Wilczek in 2012. And time variable crystals is not a time crystal. I'm sorry, this is my view.
Well, I agree, but I guess there's a community, and we agree what we mean when we say photonic time crystals.
No, well,
it's just time-varying structures.
Yeah, so the time crystal is a system which spontaneously transfers into the state of persistent motion.
Yes.
This is what you are talking is time variable crystal. It's great work, but please sort of note my view on that.
Yes. Yes, this is not time crystals in the original sense. That's, I agree.
Sasha,
yes.
Question. Great talk. I want to know something. Can you do the equivalent of modulation doping for your structures? Because, you are changing all these things by changing the thickness, but equivalent, for example, it's well known in certain modulation dope system, you can transition into the Wigner crystal just by changing the density in this modulation doping. Plus, you can do gating.
Yes.
So the question is dual. Can you do modulation doping and can you do gating?
That's what we would love to do, because obviously you're you're right on, spot on. So playing around with thickness just gives us kind of a good starting point, because we want to hit this regime where we are sitting in the Wigner crystallization stage on the phase diagram. But when you are there, you can do other things like gating, for example, to change, because sitting on the near this kind of phase transition between the Wigner crystal and the point where it's melting would actually give us a lot of opportunity for active tuning. And we just discussed it with Eli yesterday, that that's actually something very interesting to see. So we would love to explore that, and we will.
You could get the actual phase diagram.
Well, we do have phase diagram. Igor has a phase diagram. We do have it. The only thing we need is a good quality materials and the good starting point. We have the starting point for hafnium nitride. We know that it can be seen in titanium and zirconium nitride as well for a thinner film, so maybe a slightly lower temperature. But we have it. We have a phase diagram, and we know exactly where we have to be to actually be extremely sensitive to these changes, to switch between the crystallization and melted crystal stage.
Sorry, in electron phonon interaction, when you go to very thin materials, you said the electrons actually freeze. What happened to the phonons? And what happens to the phonon-electron interaction? I mean, I can imagine the phonons are obviously due to the cores in the material. When they oscillate, presumably...
Well, that's why you have you are improving the effect, and you're moving to this range when you have a low temperature, because it is helping you to strengthen, so that the potential energy of electrons wins over all the other interactions in the system. And you also have to be very careful that there are no other kind of competing effects that can promote electron localization in this way.
Electron-phone interaction in 2D normally is well known, but you're looking at a point where the electrons are actually fixed. Do I understand that?
This is true, yeah. They are actually fixed because they interact so strongly with each other. So the interaction between those electrons actually outweighs other interactions, and that is what corresponds to this ground state. This is how I understand it.
But all transport phenomena are actually based on, for example, optical phonons or even acoustic phonons.
Yes.
When it's so thin, phonons are understood, but not when the electrons are crystallized. So I suspect this is something you want to go and have a look at.
Well, for sure, especially in these systems, because again, these systems are different. They are different from conventional 2D materials, so they would definitely have different properties. Yeah.
Thank you. You were showing slides, I believe, of resistivity and carrier density on very thin TiN films. Those were obtained using ellipsometry.
So the
or
resistivity.
Hall effects.
Hall effect. Yeah, that was
Okay.
Hall effect for the hafnium nitride. Yeah.
Right.
These are based on Hall effect.
In those ultra-thin films, be it hafnium nitride or TiN, when you're down to the 1 to 2 nanometer range, surface scattering effects start to become important on
Yes,
transport
yes.
properties.
Yes, absolutely.
Was that factored in any way in trying to come up with the resistivity of the film and importantly, the electron density?
Yeah, so actually the quality of the film and the scattering effects are very, very important on all fronts. Just to start with, it's anything happening on the surface is extremely important for characterization of this ultra-thin regime. Well, first of all, you have to account it just for ellipsometry measurements, right? Just to retrieve the change of the optical properties. You have to make sure that you know what happens or protect the surface. So high quality films is exactly what we need because for Wigner crystallization, actually one of the outstanding questions is how to distinguish it with localization which is related to disorder. So any types of disorder in the system could actually drive the localization of electrons as well. So there are many effects that we will have to take into account. And the starting point is, yes, to ensure that we have high quality, like epitaxial film, and there are also ways to protect the surface so that we avoid all these effects.
Thank you.
So the time is up. We have to move on. Let's thank Professor Boltasseva. Thank you very much for the wonderful talk.